All right, sorry for that. Our microphone wasn't working. All right, so this chapter is redox reactions. So again, everything's kind of piling up, but this should hopefully reinforce our oxidation states and make us feel more comfortable about all that. And so we've seen this before. We've talked about these types of reactions. We just haven't realized it yet. And so oxidation reduction reactions, which are just called redox, you'll see for short. So redox reactions are just any reaction in which electrons are transferred. And so what was one case that we looked early on that was electrons being transferred? So ions, but yeah, so what do we make? What two reagents that we put together that made a simple ions? Or even other reactions that we might have done? Yeah, so non-metal and a metal, but what was a specific reaction? Yeah. That's a good one. So that's a more advanced one. So zinc plus our copper sulfate. So that's one example of a redox reaction. Excellent. Other ones that we've seen, other basic ones. And we'll break down how this was a redox reaction. Of course, your clues of metal exchanging is always a good one, but we'll talk about that. What are some other examples? Redox reactions. We were talking about it, metal plus non-metal. How do we make our tasty salt in the lab? Yeah, but how do we make that? Remember two nasty elements? Yeah, so just sodium, and then we know chlorine's a diatomic. So, right, this is kind of helping us with chapter 5 too. Remember how to piece things back together. So this is another redox reaction example. Good, and we remember that, right? We remember that sodium gave up an electron to chlorine, and that's how we made our cation and anion. So just kind of recall, right? We had our sodium with our Lewis dot structure, and then it lost an electron, and meanwhile chlorine gained that electron. So just tying things back. All right, so let's look at other examples. So I go through how to formally identify them as redox. But again, your big clues are we have things in their elemental form or things coming out of a compound into their elemental form. So that's always a good kind of clue. And so many redox reactions involve the reaction of substances with oxygen. So this means, right, your combustion reaction is also going to be a redox reaction. And that's, again, sometimes the definition of oxidation reduction. And we'll look at the true definition, but just kind of the alt definition is if you add oxygens, you oxidize, and then add hydrogens, reduce. But we'll come back to this concept. So this is just really broad to, again, sometimes clue you in, but this isn't the true definition. And again, we can see other examples. So iron rusting, again, you see two elements coming together. We mentioned our combustion, and so there's, right, our clue, our carbon became oxidized with a bunch of oxygens, and then oxygen added hydrogen to it. Here's another simple combustion and redox. And so again, the concept is if one atom loses an electron, another must accept them. And so this also means that our redox reactions must be balanced. And so that's something else that we'll look at. So we must balance our electrons. So if you have 6 electrons being donated, right, 6 electrons have to be accepted from somewhere. And so now here's a true definition of oxidized or reduced. So atoms that lose electrons are being oxidized. And so that means that they underwent oxidation. And then atoms that gained electrons are being reduced. And so we also see this, we can add to this definition. So if it's being oxidized, that means it's the reducing agent. Again, meaning it's supplying the electrons. And so what type of elements do you think are going to tend to be oxidized or undergo oxidation? So other way around. Although, so the D block would also potentially be oxidized. Not the P block. So who's giving up the electrons? Who has all the positive oxidation state? So yeah, mainly our S block, right? So we're thinking our metals, so our alkali metals, right? Just think of Na plus. So that means, right, sodium is your reducing agent, the elemental form, and then it gets reduced to sodium. So it's losing electrons, so you see, right, follows that. So group 2, same thing. And then you did mention the D block, so right, don't forget about that.
Yeah,
so,
but it was an accident.
Well, it was a correct accident. So
it's S block and the D block?
yeah, so any of our metals, right? And again, we're looking at metals in their elemental form. So that's what we're looking for when we say that they're supplying the electrons, is it has to be the metal in the elemental form, right? So that's like nickel metal, iron metal, whatever. So we could go on and on, list the entire D block. So all those generally supply electrons. And again, you can see that on your periodic table, right, with the plus oxidation states that they like to be in. And so then that means atoms that gain electrons are being reduced. And so now which block?
P block.
Yeah, so this is the P block. So P block, right, so all those ones with our negative oxidation state. So obviously the halogens. So right, group 6 for sure.
So are they the receiving agent? Or what do you say with that? Instead of reducing
Oxidizing. Oxidizing agent.
means they're the receiving?
Yeah, so they receive the electrons, so they're being reduced. And so let's go through.
That's just weird. If they receive the electrons, they're called oxidizing.
Oxidizing agent, yeah. They do the oxidizing. So hang on. Let's skip down to the rules for assigning oxidation states, and then we'll do some practices, but they're fairly straightforward. So rule number 1 is free elements always have an oxidation state of 0, right? So this just means in their elemental form. And so diatomics, they would be 0, right? S8, still 0. So sodium metal 0. So again, anything in their elemental form just starts off as 0. And then we know from our periodic table trends, so we can then figure out what their oxidation state would be just based upon the charge that they like to be. So sodium's going to be +1, chlorine's going to be -1. So that should feel like the same, right? So it's kind of repetitive.
When you say elemental form, you're just meaning when they're by themselves?
Yeah. And so sometimes, right, you have to look at your compound to figure out what the oxidation state would be. And so one of those funky ones, and we'll look at some example. So rule 3 would be the sum of the oxidation states of all the atoms in a polyatomic ion equals the charge. And we've seen that before, right? We've said, well, all our charges have to add up. Usually we look at neutral compounds. And so in this case, if we're looking at nitrate, then you have to kind of base it off your other ones. And so part of your rules are, these are usually your oxidation state priorities. So meaning fluorine should always be -1. Hydrogen is usually +1, right? But we remember that there are some exceptions with the hydrides. I think you had some metal hydrides on your naming. So that's rare. But again, usually hydrogen is +1, like in an organic compound. So it's usually +1. And then this is really important. So oxygen is usually -2. And so this is why we base a lot of our oxidation states off of oxygen. And again, the only exception is when O2 is like that, such as in a peroxide. And a peroxide just has this general layout. So it's just an O double bond, or O bonded to itself, so 2 oxygens. So that's a peroxide, but that's only when, like, hydrogen peroxide, you wouldn't be worried about organic peroxides. All right, so back to this example. So if we know oxygen is -2, then we can follow, so they laid out the algebra over here. So the overall charge is -1, so that's why they set it equal to -1. And then this is for our oxygen. So they plugged in, well, we have 3 oxygens with a -2 charge equals 1. So, right, you just have x plus -6 equals -1. And so now we can solve, so x equals 5. So that's all they did there. And so that's how we know some of these ones like nitrogen, phosphorus, sulfur, where they can be funky and positive and negative oxidation states. So we have to base it upon the other elements. Does that make sense for those? And again, the ones that you can always point to that you know are going to be the same are your group 1. So we know, right, those are always 1+. So sodium, potassium, rubidium, cesium. So that helps you. We know our group 2 metals are always 2+. And again, we've seen that. We've practiced that. And then again, we have our priority of our oxidation states of how you'd want to assign them, and then base your other ones off of that. So let's go back and let's go through, well, how do we determine whether it's a redox reaction? And so the first thing that we can do, so we're looking at sodium plus chlorine gas gives us sodium chloride. And so we want to just write our oxidation states with a solid. I probably should have put aqueous. But solid.
Oh, salt, got it.
So what's the oxidation state of sodium? But it's by itself, right? Yeah, so it's 0. It's in its elemental form here. And what about chlorine? What's its oxidation state?
Well, I thought it was -2, but apparently it's not.
Oh, because what form is it in? Yep,
Why is it 0?
because it's in its elemental form. So, right, chlorine's a diatomic, and it's in the gaseous state as well. So it's just as the element.
Okay, is that just some rule that you know what it is?
We did mention the diatomics, right? So I don't know what rule you missed, but right,
I still don't, I'm not following line 0.
that's just the rule. Anytime it's in its elemental form, it's 0 for the oxidation state.
Okay.
But then we have to know that chlorine is a diatomic, so then we recognize that's in its elemental form.
Okay.
So you should have hopefully highlighted the diatomics. If not, we could do that.
Ene and
That's the ending of the halogens, ide. But what are the 7 diatomics? And iodine. Yeah. So yeah, oh, I don't have a periodic table on this one, but I would again just highlight them. If you haven't done so, yeah, it just makes the L plus your hydrogen. Of course, now I can't find, oh. So that's what I mean, everything starts coming back to haunt us, because we have to remember that, or, so now we can take our highlighter, right, so just highlight those 7 diatomics for yourself, so you always remember. All right, so back to here, and so now that we have sodium and chlorine in a compound, so what's the oxidation state of sodium here?
is carbon the diatomic?
No.
Can you go back to that highlight list real quick? Nitrogen.
And then hydrogen.
Oh, there it is, got it.
What are those called again?
Your diatomic.
Diatomic, that's what it was, okay.
Yeah, because we also had a lab that like
Yep.
went over it.
I just forgot the wording of it.
Oh, you're fine. So then what's sodium's oxidation state here?
So would it be zero still, or no?
No, so now it's in, yeah, so now it's in our +1, because it's in a compound.
Diatomic.
And then what about chlorine? So now it's in a compound. Yeah, -1, remember? So they,
Because the -1 gains electrons, okay.
yeah,
So real quick, just so my brain can process this, in the elemental state, there's no oxidization happening, so it'll always be 0, right? But once you stick them together, you have to understand which one's giving up, which one's receiving.
yeah, essentially, yeah.
Cool.
So now, yeah, so now you got it. So elemental state is just, yeah, your starting point, and now you're figuring out gaining, losing. And so now we can see, and now we're just going to more formally chart this out. And so now we can really see who gained, who lost. So we went from a 0 to a +1. And so does that mean we gained or lost electrons? So lost electrons, and we'll put 1 in this, well, 1 times 2. So really, it's a 2-electron process. So this is what we want to see is, so it's 1 electron change, but then it's 2 equivalents, right, from our balanced equation, because now balancing is going to come into play, because we have to make sure our electrons are balanced. And so, of course, we need to have 2 electron action coming and receiving. So now we went from 0 to -1. So now we gained at least 1 electron in our process times 2, because there's 2 chlorines, so 2 electrons now. So does that make sense for that first example?
Do we need to put 2 dots on the 2 electrons dot dot? Is that because there's 2 of them? Oh, never mind. 2 because of the coefficient is 2?
Yeah, so you have to make sure everything's balanced at the end. Right, so even though each chlorine itself is just gaining 1 electron, we have to examine that there's 2 chlorines, right? And we have 2 in the final reaction as well. And so there has to be 2 electrons total then in the balanced equation. So let's do some more examples. And again, we're just identifying. So oxidation is an increase in oxidation state, reduction is a decrease. And there's also more mnemonics to help us remember. So I'll give you 2 that are kind of helpful cheats. So the first one I'll start with, so I learned this one originally since I grew up in Texas, and of course I like the oil industry. So we can say, so oxidation is losing electrons, and reduction is gaining. So that helps. And so maybe you don't like the oil industry, not a fan. That's fine. So we have another mnemonic to help. So we have Leo. And this is where you have to insert your favorite cuddly tiger or whatever. I used to do Leo the leopard because that was my old school's mascot. But Leo the leopard goes grr, or Leo the lion. And so that's just losing electrons is oxidation. And gaining electrons is reduction. So that usually helps people kind of remember, right? You can slap those down on an exam so you don't get them backwards. Make sure everyone finishes. Do we finish with this part? Are we still copying? No. All right. And so we'll just be practicing this, right? Identifying who's being oxidized, who's reduced. And so in this one, we can just go through their little example. So we have a combination reaction. So again, a good indication. We have a redox reaction, 2 things in their elemental form, and then combining. So once again, they're at 0 oxidation states to begin with. And then they make CS2. And so you'd want to base it off the sulfur first. So you start with sulfur. Okay, that's probably -2. And then that means your carbon has to be +4 then. So you don't want to do the other way around since carbon can be too many other oxidation states. So carbon is really flexible. And then kind of as an aside, while we're talking about carbon, so carbon can also formally have like partial oxidation states. So, 1.5, 2.5. And so for our sake, we'll just kind of accept that. If we were to go on, we would actually have to look at the molecule individually and analyze each, carbon bond and kind of figure out what the oxidation state of that carbon is. Because it usually doesn't mean that you really have a 2.5 oxidation state. It's that, one's at 1, the other's at 3, or they kind of average. So, and of course, if you have multiple carbons, that makes it confusing in some ways. But again, you could break it down, but we probably won't go there in this class. Excellent. And so again, oxidation states. So this is, again, more formal bookkeeping for our sake. And so this is just saying if they don't involve oxygen, right, we just have to assign oxidation states. And so even though it looks like it, oxidation states are not ion charges. And again, they follow along. They're the same. And for our purposes, right, they're the same. They're just emphasizing here, right, an ion would be something that we can measure, right, you can calculate. For example, you have sodium chloride, so you could calculate, right, the charge between them. But then once you talk about oxidation states, it's kind of more like electron counting bookkeeping. So this is really for bookkeeping measurements. I'll say bookkeeping. All right, again, just making sure that we have enough reagent as well, because again, we mentioned we have to balance reactions. All right. So blah, blah, blah. So we kind of skipped that, or we did look at that. And so then this is just formally emphasizing that we assign them. So again, a reactant that reduces an element is called your reducing agent, and it is oxidizo. Again, thinking of your metals. So those are always going to be your reducing agents. You see that in the chemical literature, that term is thrown out a lot. And then the reactant that oxidizes an element in another reactant is called the oxidizing agent. So again, we saw that, so that's going to be reduced, receiving those electrons, like chlorine gas is a good oxidizing agent, or obviously oxygen is an oxidizing agent. And going back to the hazard symbols, sometimes you'll see, oh my goodness, I can't even draw a square, a triangle today. But you have the oxidizer symbol, so that's going to be something that's pretty reactive as well. So anything that has that oxidizer symbol, you would also want to store separately. So these are pretty nasty reagents if they're strong oxidizing agents.
So they're the cause for the oxidization then. Does that make sense?
Kind of, well, there you get into, but we don't want to get into like the whole rabbit hole, but like in a sense, yeah. So you have kind of this push and pull, but almost what you're alluding to is what you can have is like your reduction potential. And this gets into like more mathy parts of it, but essentially there are more elements that are like stronger for reducing. And so you'd have to like measure their reduction potentials like with a battery. So it's kind of like making a cell. But yeah, so essentially if you have something that's either a really strong reducing agent or a strong oxidizing agent, that could be a good indication of a reaction that's going to happen. But that gets into like kind of other things as well, which we're kind of touching on, but dancing around. Yeah, we're like not quite there, but you're kind of at the right idea that there has to be some sort of, think of it as like a chemical waterfall, right? Like there has to be some energy that's going to be likely gained to make your reaction go. So now we're kind of talking about thermodynamics. All right, so now we are going to kind of transition to thermodynamics, but still not where you're taking it. Yeah, I like all the questions. And so now we're talking about the nature of energy, work, and heat. And so we are going to be getting a little into it, but like I said, not where you're at yet, or where you're asking. And so this is just basic thermodynamic concepts. So energy is just defined as the capacity to do work. And so this could be, right, kinetic energy, so running across, right, pushing a chair. This is performing work, right? Or it could be, right, potential energy. So we're going to talk a lot about potential energy. And so we're really looking at like potential energy and bonds, but how you can think of it is you have, right, your lovely snack over there. So that's going to be converted, so that's potential energy. Then you're going to, of course, eat it, and it'll eventually become your mechanical energy, right? So all that process. And we also know, so energy, of course, can be exchanged through objects, through contact, through collisions, and of course, performing work. And so what is work? So work, I know work is actually defined as force acting over a distance. So again, that's why I moved the chair. So you have to apply a force. And then heat is the flow of energy caused by a difference in temperature. And temperature is just directly proportional to the kinetic energy. And so heat and work are the kind of the two main ways that an object can exchange energy with other objects, either in or out. So like gases can expand, for example, so that would be like the gas performing work against the environment. And obviously we have heat flow. And so you may be aware of some of these definitions. So kinetic energy is energy of motion, or energy that is being transferred, right? And so we know that. So we can hold our pen in the air. So right now it has potential energy, but as soon as I release it, right, it has kinetic energy, so energy in motion. And so thermal energy is again associated with temperature. So again, due to our molecular motion. And so we should just add in here, other forms of kinetic energy are like electron movement, like in a circuit. So that's also just kinetic energy. It's just those electrons literally moving around. And so like I mentioned, so we are going to be looking at potential energy a lot. And so of course you might know about positional potential energy. So again, due to your gravitational potential, of course gravity is pulling down. So that's one form of potential energy. But like I mentioned, we're going to be interested in the energy of bonds. So right, literally how much energy is in every bond, how much energy does it take to make and break bonds. That's really where we're going with that on our level. And so now just different forms of energy. So again, I mentioned electrical. So electrical is often forgotten. So that's just, again, kinetic energy associated with your flow of electricity. We mentioned heat before. So again, just kinetic energy associated with motion. Light or radiant energy. So that's going to be associated with energy transition. So y'all are familiar with that, right? The fire. Yay, fire. So that's all electrons, right? So you get to see that form of energy, the energy being released as light. And so nuclear, of course, this is another form. So this would be potential energy that's stored up. And obviously, right, those nuclear reactions are very energy dense. And so this would be a great form of energy. And then again, chemical energy, we're looking at your potential energy due to our structure of atoms and how all that relates. So some units, so we can follow units. So you may be familiar with this formula from physics in a past life or something. And so this is just kinetic energy is 1/2 times your mass velocity squared. And then in physics, right, mass is usually given in kilograms, and velocity, so velocity is going to be meters per second. So just plugging those units in for kinetic energy gives you this. So I'm just going to rewrite that over here. So kilogram, meter squared over second squared. And that's just equal to a joule. So that's convenient for you. And sometimes you might also see this unit of Newton meters. So you see this referred to in other places. Know that this is what it's related to. So I don't think we use Newton meters too much in chemistry, but probably if you did take some physics, or again, you're reading a paper, Newton meters might come up. So yeah, different industries use different units. So 1 joule of energy is just defined as the amount of energy then needed to move 1 kilogram mass at a speed of 1 meter per second. And then, so this is the part where I think everyone always gets a little depressed. So 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Here's the depressing part. So this is not a food calorie that you read on the box. Yeah, so your food calorie is equal to 1,000 of these calories, or 1 kcal. So now that's defined as the energy needed to raise 1,000 grams of water, 1 degree Celsius. So you can think about that right next time you eat your bag of chips. It's kind of frightening sometimes, but whatever. Don't obsess too much about calories. But but yeah, you can also just see that energy, right? Like just like burn a potato chip one day and just like like seriously marvel at like how long it burns for, like all those fat, those calories, like that's energy.
Those really weird life hack videos had fire starters with bags of chips. So.
Yes. See?
We used to do a lab in high school where you took an almond and you lit it on fire and then you put it underneath the beaker and you did the temp change of the water and you could actually do the calculation.
Yeah.
To figure out how many calories are in
Yeah.
one almond.
Yeah, you can totally do it, and you can do that with any substance. Like, yeah.
Because that's actually how to figure out how many calories are in certain food.
Yeah.
You're burning everything.
Or like, it's mainly the sugar.
Yeah,
That's right.
So it depends. Yeah, like if it's a drink, then it's just like, well, how much sugar and how much burn? Yeah.
So, how much calories is that?
I know they have a base index for most ingredients and they just do the math.
Yeah.
Go back to the old days, lighting stuff on fire.
Anyways, yeah, if you get bored, you could set up your own.
Marshmallows are an easy one to do.
I know. Are we doing s'mores on Wednesday, by the way? I was thinking I shouldn't bring them today because we won't be in lab, but should we do s'mores? Did you bring sticks?
That's good because I completely forgot about the stick thing.
Okay,
So, I will bring them Wednesday.
let's plan for Wednesday. It's a better lab day. And then we can maybe burn one. No. I mean, we can. We can be like, look at all the energy we could have quantified. No.
Look at all the energy we could have had.
Yes, in our bodies. No. Yeah, see? I like the spirit. Anyways, depending how bored we get in lab, we can calculate it, right? We can do the math. We have the ability, we have the knowledge. The hardest part is just trying to make your system as closed as possible to capture all that heat. Anyways, moving forward or inching forward here. So more units, so we'll see this a lot, this is probably a unit you'd want to know, joules, and this is kind of related to the specific heat of water, since water takes 4.184 joules per gram to change the temperature, so high specific heat. And then we mentioned again our kilocalories, and 1 food calorie is 1 kcal, or 1,000 calories, so now we're all going to be getting depressed about that.
Are you gonna get sheets for that?
I wasn't
Write it down.
planning on it. Yeah, and probably on an exam, I would just like give you the conversion. So this is more like what you might see, because we don't tend to use like kilocalories or food calories too much. But I'd probably just like give you some conversion. Like, remember that 1,000 of our small calories was 1 food cal. Yeah, I don't expect you to remember all that. All right, so then we should know, though, about our first law of thermodynamics and our conservation of energy. So the first law of thermodynamics is the law of conservation of energy. And so all that means is the total amount of energy in the universe is constant, so it is conserved. And so that's right, we can't design a system to produce energy without some sort of source of energy. And y'all are familiar with those concepts, right? Like the perpetual motion machine, so that like thermodynamically doesn't work. Yeah. And then are y'all familiar with the theory of the heat death of the universe?
The what?
If you get really bored at night and want
Oh,
to
God.
think existential thoughts of like the universe,
Traumatize yourself a little bit. Well, no, like, okay, so I have a question. If a star, if you can't create or destroy energy in a star that's emitting light energy and heat energy, what happens when it runs out of energy that it has?
I shall probably be dead by then.
well, stars do explode, so we do know that. But then what happens after it explodes? Like then, so that's like the heat death of the universe is essentially, right? Is because you're always losing some amount of energy efficiency
You're
as
always
heat
losing
and
time.
light. Yeah.
Time is always running out.
But then, this gets into, a lot bigger questions.
They've actually figured out that a lot of the times that stars go in either implode or explode is due to the fact that they lose enough energy that they no longer have the ability to maintain their state of form, which they just wipe out their entire solar system.
I don't know if they wipe out the whole solar system. They
Not
just
the solar,
explode.
yeah, isn't that their solar system?
Well, I mean, they explode, but I don't think it would wipe out it would wipe out the life, if any life depended on, like, that sun.
Because, like, I mean, our sun, they did the math, so if ours exploded, it would be big enough that it would actually reach past Pluto and just
Oh, man.
incinerate all the planets in our solar system.
Oh, I'm not sure. Maybe I could totally be wrong, but.
Some of them, but it also depends because there's different types. There's red giants. It depends on what kind of explosion it has. Anyways,
Yeah, I mean, so basically what this is leading to, so you can kind of read the theory, but it's just, at some point over some time, so like if, in infinite, like who knows how many more million, billion years with this theory, that basically you'll approach a state where all energy is like evenly distributed, so you can't perform work anymore. But who knows?
It's our descendants' problem.
Yeah.
Exactly.
And I mean, there are some questions about whether this would actually even happen, and it also assumes, I think, that the universe isn't moving, so I think they say,
and they also have to think that the biggest counter to that is they've actually seen stars created after the explosions of other stars, and so they're trying to figure out. They don't know how stars are forcing themselves to become two, but that's beside the point.
yeah, I mean, it's crazy stuff to think about, so you can dive into it and think about it when you're bored at night, but Yeah, because there's a lot of questions of, is the universe expanding or not, and at what rate it is, and then will it expand forever? Will it reach a contraction point? So nobody knows all these things, so that also has a lot of questions about our energy and our system. But
My prediction is that we're gonna meet aliens first before we ever have any sort of big explosion or whatever, like.
yeah, I'm so like not on board with the alien thing. Like,
Oh, you don't believe like government that they just did a press release that they're taking?
no, I think it's just a distraction.
Oh, we're not getting, okay. It's a beautiful day outside.
Anyways, bond energies. Back to what we do know. We do know at least about bond energies. And so chemical reactions, the beauty of them is they all involve either breaking bonds in our reactant molecules and then, of course, making new ones to create the products. And so this means that we can also predict what's called our delta H, so our change in enthalpy of our reaction. So basically, does the reaction get hot? Does the reaction get cold? And now we can start thinking about other ways to relate this. So this means we can think about, well, if the reaction could be hot or cold, maybe that's what they put in like your hand warmers that I'm sure you'll be using once the winter season approaches, right? So what chemical reaction is that? What dictates that? Or those ice packs, right? You've probably seen them, you break them, and they get cold. Well, what drives all of that? So that helps give you an idea of again, your enthalpy, so you can calculate it and then know why reactions turn hot or cold.
What about with icy hot, where it feels like it's hot and cold at the same time?
Yeah, it's like the same sort of thing. I have to look up because a lot of it is from the menthol too, which gives you that weird sensation of like burning icy. But yeah, just like similar concepts. So either trying to figure out reaction or like how it evaporates and feels to you.
Menthol and cigarettes, or am I way off?
There are menthol flavored cigarettes.
Oh, okay.
So not every cigarette has menthol.
They even have a little popper.
Yeah, those are the best ones. Don't smoke. Don't smoke, guys.
But you do smoke.
If you did smoke. Anyways. And so the amount of energy it takes, and again, this is more formal definition, to break one mole of bond in a compound is called a bond energy. And so this is how they calculate it. They calculate it in the gas state where they try to do that. And they do these, when they calculate it, they assume a homolytic bond or at least get it to react homolytically. And again, all that means is each atom gets half of their bonding electrons. So, right, we have 2 electrons here. And so if they break homolytically, we use these little half arrows to indicate 1 electron movement. And so it just breaks like that. So just a normal, the other word is just a normal bond. And I'll versus heterolytic, which would be uneven, but not necessarily concerned about that right now. And so your actual bond energy depends on your surrounding atoms and other factors, but of course we can at least use our average bond energy to estimate the delta H of our reaction. And it works best when all reactants and products are in the gas state, but you can also calculate it for other states. And so this is really important because we'll have to do some of this. And so bond breaking is endothermic, meaning that you gain energy from it, so it's going to be a positive value. We're breaking bonds, we're getting that energy. But then if you make bonds, it's exothermic. Oh, I think I said that backwards. So breaking bonds is endothermic, so it requires energy. Sorry. Got overexcited. And so that's a positive value. So again, you're putting energy in to break those bonds. Exothermic, so making is usually favorable. And so that's where you gain energy. And you get a negative value. And so then we can calculate the delta H of our reaction by adding up bonds broken plus bonds formed, and then figure out how much energy you had to put in overall or take away. And so just in general, so we'll look at some trends, but on an exam, I would either give you a chart or like give you all the bond energies you would need to know. And then we can just kind of compare trends. So in general, right, the more electrons two atoms share, the stronger the bond. That makes sense. And so again, these are just averages. So like a carbon-carbon triple bond goes all the way up to 837 kilojoules versus a carbon-carbon, 347. And then again, you can compare your carbon-nitrogen triple bond is pretty high at 891 versus your single bond, 305. And then in general, the shorter the covalent bond, the stronger. Again, that also makes sense. So we can compare, so your bromine-fluorine bond, where fluorine is a lot smaller, just physically, is 237 versus bromine-bromine, which is 193. And so, right, bonds get weaker down a column. That makes sense as they get kind of bigger, but then they get stronger across the period, or tend to, so thinking of your electronegativity trend. Negativity. And so again, you would need to reference a chart. So for these examples, I'll be scrolling around this chart. Make one note. So your CO bond in carbon monoxide has a special value. So notice, right, your C double bond to oxygen is usually 736 in other organic compounds, but in our CO2, it's 799. So just note that value. All right, so now we're going to look at this reaction, and we'll quantify this. So let's quantify this one, and we'll do the practice. And so let's look at this reaction over here. So we'll examine what's going on. And I'm just going to, where do I want to draw it out? I'll draw it out on the side here for now. And I'm going to draw it out kind of explicitly. So we're starting with methane. And I'm just trying to draw it so we can see the bonds right now. Plus chlorine. Oops. And let me give myself more space. So it gives us, so it looks like we're swapping. So we're breaking, so we're trying to identify what we're breaking. So we're breaking this chlorine-chlorine bond. Then one chlorine's going on here. So it looks like we'll have to break a carbon-hydrogen. So we'll kind of identify our differences. Then we also make HCl. And so at this point, right, identify what bonds are being broken. So we need to break a CH bond formally. We need to break a chlorine-chlorine bond. And then we're going to make this carbon-chlorine and make hydrogen-chlorine. So does that make sense? You're just kind of identifying what changed, and then of course the quantities. So if this was using like multiple equivalents, we'd need to take that into account. And so now let's do the accounting for it. So let's do bonds broken first. So we need to put energy into the system. And so now let's look up CH bond. So we'll go to our chart. CH, a regular single bond is 414, and that's kilojoules per mole. And so there's just one of them, so that's fine. And then chlorine, there's my chlorine. So chlorine, so 243. So we'll add those up. Yep, and pull up my calculator. So I get 657, and so that's kilojoules. So again, that's positive, right? Energy going in to break those bonds. So now let's see how much energy we get out. So bonds formed. And so first I'm going to add them and then put a negative sign on all our bonds formed. So then we look up carbon chlorine. So 339. Then we need to look up hydrogen chlorine. So 431. So let's add those up. And so now this is energy that's favorable or gained back. So it's 770, but then I'm going to put a negative 770 because again, it's bonds formed, so it's releasing energy. And so to find our overall delta H of our reaction, we can just add these two. So 657 kilojoules plus my negative 770 kilojoules. So I get an overall enthalpy of negative 113. So delta H is negative 113 kilojoules. And we are getting there, but we'll learn that this is exothermic. So it's releasing heat. And usually exothermic reactions are more favorable since they're releasing heat, so they tend to be spontaneous. That being said, endothermic reactions do exist and go.
So would exothermic just be more natural in the fact that having excess heat is easier to just shed the excess energy than like having to find a source of sucking heat?
Yeah, that's generally, yeah. And so like thinking about sucking in heat though, so that's why your cold pack does feel cold though, right? Because it is using your body heat to power that little reaction versus, yeah, an exothermic where it's just like go, boom. And sometimes, exothermic reactions tend to be like faster for that reason.
So are some endothermic reactions, do they not naturally, is that why some take heat in order to activate the reaction? Is because they're so endothermic, they need the heat, the energy to
Yeah,
force the reaction?
yeah. And so part of the issue though, so like you're totally on the right track, and then it's just right now we're only seeing like a small part of the picture too, because overall you'd want to calculate what's called like your Gibbs free energy, and that tells you truly whether a reaction would happen or not. So right now we're just looking at enthalpy, but then we have to look into like how spontaneous it is. So like there's certain conditions which make reactions more favorable, like different states or making more moles. Like anything that creates chaos is favorable versus like creating less moles, that's more ordered, so that's more entropic. But yeah. So I was just gonna say, we look at that in like the 200 series, so take it like all the way. But yeah, that's, your basic question is correct.
Okay.
Can you repeat why you made the 770 negative again?
Because it's bonds formed, so formally, when you form a bond, it's like dropping the energy level lower, so usually that means you get energy back out. And so this is like your bookkeeping now, so that it just means thermodynamically, you're getting energy out, so that's favorable versus having to supply energy. So yeah, bond formation is always
That's
exothermic.
releasing energy.
Yeah. So anytime you have bond formation, it's exothermic. You're just seeing, is your overall reaction then endothermic or exothermic? All right, so we feel okay about this example? So let's try this on your own, but I'll have you, so you probably want to copy down the reaction and then I'll scroll back up so you can see all the values. So it's just methane plus water gives us hydrogen and CO2.
So, that's a question, are we, you might have already answered this, Stacy, are we gonna get a chart that has that stuff on it?
Yeah, either you'll get a chart, or what I usually do in an exam is just like give you a small
Whatever we're
info.
gonna
Yeah,
use.
it's like these are all the relevant bond energies. Yeah. I'm just trying to find. There we go. Mark here. I'll rewrite it on the board just in case. So I'll scroll back up. Okay. Oh no. Sorry. Okay. Got an
Oh,
answer?
no, I don't even know how to start, so.
Don't know how to start?
No.
Well, my question is, I don't know if I'm just being super spacey today, but for like the CH4, do you now have 4 CH reactions on the one side?
Exactly.
Okay, and then would you have 4 OH reactions because you have H2O times 2?
Well, for that one, then you'd count it as a double bond. So that would,
So technically, okay, so there's, so I would add, okay. Well, the H2O?
so then the H2O, yeah, that would be
H2O would
2,
just be
yeah.
4, right?
Yeah, that would be 4. So you have to calculate how many 4 OH bonds, yeah.
Okay, so then the only one that would be a double bond would be the CO2, right? So
Yeah.
it's 2 double bonded COs, right?
Yeah. So let's,
Can you scroll back up for like?
oh, sorry,
No, no, no.
scrolling everywhere.
Okay, so that's what it was. I grabbed the wrong CO.
Oh, yeah, so you wanted this CO as,
Yep.
yeah. That was, so where you should have started, so hopefully the idea was you could at least write this out, right? So that's where you want to start, is just like, you know, redrawing what we have there, maybe as a visual to help you. That would be like the first step, if you're, especially if you're lost, right? Is just, and be explicit.
How do you draw out the 2H, H2O?
I would literally draw out 2 if you have to, right, to help you. So if you're really not seeing it, right, draw it all out so you can. So you have literally 2 H2O drawn out. And then draw out 4 H2s if you need to, right? So you can see. Okay. And then my CO2. So now we have everything drawn out. And then this is where, you know, you can start highlighting like, oh man, I have to break all those CH bonds. And you could, you know, do your calculation. So I know I have 4 CH bonds, so I need to get that times 4. So 464 times 4, it sounds like. And someone can back us up. And then, right, and then 4 OH bonds that you have to break. So 414 per OH bond. Right, so then bonds broken. So just do it very step by step. We could even do the math here if we wanted. And if any of the numbers are wrong, just let me know. So like 3,512 kilojoules. And remember, that's positive, so we're breaking all those bonds. Now we have to see what do we get back formally. And again, right, we have to make 4 HH bonds. So 436. And then our CO, which was our special number, that was 799. Because it's special for CO2. So 736 is for like C double bond O in a compound, but CO is special of 799. It's like, yeah. That's why in an exam I just tell you it's 799 for that one point.
I could not read that.
No, I know. I made a note of it in lecture, but it's fine. So 4 times 436. Oops.
So for the 799 then, is it, oh, so it's times 2.
Yeah, and then we get So negative 3342. And so it looks like overall this reaction is going to be endothermic, right? It requires energy. So now we'll add them. So I made my bonds form negative, since that's formally negative, plus 5, 3, 5, 1, 2. So I get a delta H of our reaction of 170 kilojoules. Is that what other people got? Questions?
You're saying this one's endothermic because it's positive?
Yes. Yeah, so it requires some heat to get going. Do we feel okay that or questions, comments? Okay, we'll keep proceeding. Just let me know if there are questions. Oh, man. I left your quiz somewhere. Oh, we still have time. All right, so we have these energy diagrams, and so they're just another way of showing us what these processes are, endothermic, exothermic, and just showing us energy flow. And so if we have an exothermic process, and again, we can put under here, right? This means it's going to feel hot to us. We're going to feel that energy coming off if we're holding that reaction. And so looking at this case, so we have carbon plus oxygen oxidizes to give us CO2. And so in this case, from our energy diagram, if it's exothermic, your reactants are higher in energy than your products. And then this energy gets released as, like we said, heat. And you see that given off. So again, internal energy, so it's going from a higher energy state to a lower energy state as well. So that tends to be more thermodynamically favorable.
So are all combinations for the most part going to be exothermic?
I feel like a lot of them are because they tend to be oxidizing, like either combustions or sulfur, right, is right under oxygen, so it tends to be very oxidizing as well.
Because you don't really have any reactions on your left side, which isn't going to give you like CO, carbon and oxygen like that. Do you even have any, you wouldn't have any reaction on the left side, would you? So it just only be on the right side.
Yeah, I mean, so you're also,
not breaking any bonds, right?
yeah, because,
Only before.
yeah, and there are other like reaction things that you might be hinting at, like equilibrium. So like whether a reaction proceeds in just one direction or goes back and forth, but yeah, it gets into other things. But yeah, you're kind of right? Once it makes this and it's exothermic, it's probably not going to go back for the most part due to other factors. And so if the reactants have a lower internal energy than the products, the change in energy will be positive. And so it's just showing system, right, energy is flowing out to the surroundings. So the surroundings, again, would be your hand, so you feel it hot. And so this is another diagram, and so you may have to label one at some point. And so let's look at the different pieces. And so we have our energy activation here. And so this is kind of just the energy that any reaction needs to get going. So it could be, right, a spark to get an exothermic reaction going. So this doesn't tell you, right, whether it's exothermic or endothermic. What you're looking at is this difference here. So you're looking at the difference between your reactants and your products. And so in this case, we're looking at an exothermic reaction diagram. And so the products are going to be lower. That delta H is going to be released as heat. And then we want to just identify other parts. So this is our transition state. So this is usually fleeting, and it depends on the reaction, whether you can observe it or not, but it's just high energy transition. So endothermic is going to be the opposite. So now we have, so looking at this process, if we could do the opposite, splitting CO2 to carbon and oxygen. So this would take energy. And so looking at your reaction diagrams, in this case, our products are higher. And so again, that would take reaction, or take energy. Again, this probably is not observed. And if we have reactants have a higher internal energy, then the products, the change in energy will be negative. So hence, right, the surroundings has to supply some energy flow. So it's going to feel cold to us. We're holding an endothermic reaction. And so looking at our reaction diagram here, so again, note we have our activation energy, so that's just reactants to transition state, but our delta H is just reactants to products, and so in this case, again, endothermic reaction, products are higher in energy. And so some of y'all have also been kind of touching on the chemical kinetics of reactions. So why are things fast? Why are some slow? And so the rate of a chemical reaction is called its reaction rate. So that's just the speed, how fast it occurs. I know I said that backwards. And the issue with this is, so it has to be measured. And so again, right, while saying exothermic, endothermic, it can kind of give us a little bit of an idea, but truly to get a real picture, we have to measure that reaction rate. We have to observe it, so then we have to know like what is the rate even dependent on, so we'll get into that. And so the rate of a reaction is a measure of how fast the reaction either makes products or uses reactants. And so this is kind of the tricky part in all of this, is you also have to be able to measure this. That's not always so simple as it sounds. And so a question, you know, how are you going to do that? You can use your spectrophotometer. If there's something light sensitive, like a colored compound, so you could track it that way, but that could again be difficult. If you don't have colored compounds especially, that's not possible. You could do, right, mass spec, trying to get little aliquots at certain reaction points, but that could also have different issues. There's also NMR, so that's a good spectroscopic technique. That's always a challenge. How do you measure the reaction? And then ideally, so this is more for an industrial setting, but on the small scale could also be important too, to control your speed of the reaction. And sometimes, I've seen this with like chemical reactions like lithiation. Sometimes you want them to go really slow and keep them cold, or else they run wild. And so in general, we'll look at some factors that affect reaction rate. So in general, the higher your reactant concentration, the faster the reaction. And that makes sense. So anytime you have increasing the frequency of collisions, that means that you'll likely have a faster reaction rate. And so this also means concentration. So this could mean concentration of gases. And then we could also look at solutions, right? Which we're not quite there, but we touch on it since we do lab. But right, you could see that with your molarity. So 1 molar reacts slower than like 3 molar, 6 molar, 12 molar. So that's all concentration. Oh, so there I mentioned molarity. Temperature also plays a factor, of course. So this is just kind of what they notice. You don't have to know this, it's not that important, but just in general, for every 10 degrees rise in temperature, your speed doubles, but all we're saying is, right, temperature increases, reaction rate increases in general. So let's look at chemical equilibrium. And so now it's a lot of things, but we're just kind of looking at them in an overview. And so let's look at how hemoglobin works. We might have touched on it a little bit. So hemoglobin is a protein found in red blood cells that reacts with O2, and it's primarily iron-based. We might have discussed that before. But essentially, you have this equilibrium process. So basically, you have hemoglobin can bind with oxygen to give you this hemoglobin oxygen. And so notice our equilibrium arrows. So this is different from example for resonance arrows. So resonance shows electron movement, while equilibrium is saying, right, you have some sort of change in process. So this isn't, oops, I drew that wrong. So this is just showing resonance, aka electron movement. So we're not changing anything chemically. So this is resonance versus equilibrium. So don't confuse the two. But let's look at this reaction more in depth, or think about it. And so what it's saying is, so in your lungs, right, your lungs takes in a lot of oxygen, so it's a high oxygen environment, so it's going to favor the production of this conjugated hemoglobin oxygen. So then that leaves your lungs and floats around to your leg or whatever. And so now in your leg has already used up all the oxygen. So there's not a lot of oxygen there. So in your leg, it would be favorable to disassociate, so depositing off some oxygen in your leg or whatever. Then this hemoglobin, right, comes back to your lungs, now oxygenless, and is ready for more oxygen. So that's basically how it works. So that's where equilibrium is important. And so again, we have our arrow conventions. So just reminding you that your single arrow implies that your reactant molecules are all converted to product molecules at the end. And double-headed indicates equilibrium. And of course, you can add something like this for no reaction. I think you saw that in your lab in just a few cases. And so we at least want to be able to express the equilibrium constant. So we won't get too much into the math in this class. But we just want to be able to express our relationship. And so this means, right, we would essentially be measuring our concentrations of our reactants or products or whatever, calculating them. And then we would look at it at equilibrium, look at all the concentrations and plug our values in. And so notice our formula. And so we have this general equation here, and it's shown, so the lowercase letters represent our coefficients of our balanced equation, right? So that could be 1, 2, 3, whatever. And then it's always products over reactants, and notice, right, each one is raised to the power of its coefficient. Again, products over reactants. So the K value does not have units, so those units would cancel out if it's in like molarities or pressure. So those would be your 2 units of concentration, so it would cancel. All right, so try then, try not to reveal the answer. So try to write the equilibrium expression for that example. So 2 equivalents of N2O5 give you 4 of NO2 plus oxygen. And so wait, look at that. I'm just going to run to the bathroom really quick.
So would we do like the process above with the equation below? I'd be lying if I told I understood this entire day. Yeah. I understand that completely.
You got this?
I was hoping either makes more sense Wednesday or, yeah. I figured I would see the views on it.
Because I'm like, okay, so on you. So are you basically just,
I'm looking at the answer and I still don't know mine.
are you basically just? You guys understand this?
Oh.
Right, do we figure it out? do we get it? Right, so it's just following this, so we have, it said products over reactants. So NO2, and then usually you put it in brackets because it would be signifying molarity or some sort of quantity. And then raise that to the fourth, right, because it has a 4 there, times our other product, so O2, raised to the 1, but obviously you don't have to write it.
Exponents are back again.
Well, we're just writing it out.
I've done 3 terms of exponents.
Exponents will never leave you.
I wish they did.
N2O5 squared. So that's how you get that. And so you might have to plug in some values. So right, the next step would just be like at equilibrium. You know, NO2 has a concentration of 0.11. 2 molarity, O2 is 0.33. N2O5 is 0.45.
So what are those numbers again?
I just making them up.
Okay.
Right, I was giving.
I was like, where are you pulling from? Where am I? Where?
No, I was just giving you an example, right? So then on a test, we could say at equilibrium, whatever, and then you just plug it in. Is all I'm saying. So right, let's practice that.
But, okay, I'm confused. But how would you get numbers from the elements though?
So you can't, right? So that's the point, right? So you have to measure this. So on an exam, you make the expression, and then we just say, well, at equilibrium, here are the concentration.
Oh, they give you the concentration.
Yeah, so you'd have to be
Okay,
given
fine.
them, and then the question would be, you know, what's K?
So would you multiply those values together, like the value of n times the value of O? Or would you add them?
So you multiply, so let's plug this in. So all you do is plug it in, so now you can take my fake values. So yeah, 0.112, so then it's to the 4th, that's all we're saying, times O2, and it would have been to whatever power, but it was to the 1 anyways, so it doesn't matter, divided by 0.45 squared, and so Josh, you can tell me if you get the same thing. Yeah, I can't do that many zeros. Would you say 0.0?
0.00026, because you would still use your sig figs, right?
Yeah.
Okay.
So yeah, 2 sig figs. Yep. 1, 2, 3, 4. So 2 times 10 to the negative 4. So that would be your K. So that's all you would solve.
2.6 times 10 to the negative 4?
Yeah. So 2.6 times 10 to the negative 4.
And now that we,
So then, 1, so K equals 1.
Yeah, so now
what
you're,
does K equals 1 mean?
K equals 1 would essentially mean you have the same amount of products and reactants, roughly, at equilibrium.
Okay.
Yeah. So there's a little bit of weird squaring factor, so it kind of depends. But yeah, if they're about 1, then they're about equal products to reactants. And so let's look at these, right? What else does K imply? And again, when you're talking about this K, you want to keep it more broadly, right? Products over reactants now. And so now we can say, well, if K is greater than 1, or let's say much, much greater, so this is kind of a ridiculous example, but if we have H2 plus bromine, it gives us HBr, and this gives us a large number, apparently 1.9 times 10 to the 19th. But yeah, so all we're saying is we have a lot more products to reactants. So basically it pretty much goes to completion. So now this is kind of getting in the equilibrium factor of a reaction. So there's a lot of components to, right, studying a reaction and really optimizing it for, this would be more like for industry, right, where you care about really optimization and temperature and all these things. And then of course, right, if we have a value much less than 1, and so in this case, and this one makes sense, so if you have nitrogen plus oxygen to give us NO, if you were actually to calculate this, it would give you a K of 4.1 times 10 to the negative 31. So that implies, right, not a lot of NO, so it's mainly reactants. And that makes sense, right? Because if that reacted, nitrogen and oxygen, just spontaneously, we wouldn't have much oxygen to breathe. It would all be NO. So.
So this is just basically telling you how reactant it is and wants to be.
Yeah, so it tells you the equilibrium ultimately, right? So does it favor your products, your reactants? If it's one, then it's both. Yeah. And again,
If it's a high number, it wants to push towards the product. If it's a low number, it wants to stay in its elemental form or whatever the.
or whatever the reactants, yeah.
Okay. And then one, it just goes back and forth. It's just almost like. whatever.
Yeah, pretty much, yeah.
Got it. Cool.
I just got that part.
Yeah, so that's the basics of it. So again, I think the most math you'll probably see for your exams is, plugging in some numbers, but again, you'd have to be provided those numbers. Okay, we'll see how far we get with Le Chatelier's principle. We're kind of running out of time, but that's fine. So looking at the schedule, we're supposed to cover chapter 6 all of this week, so we can spend some time and do practice if we need. You don't have to rush, although we could.
Practice would be appreciated.
Yeah, so whatever people are struggling with. And I need to print homework, that's another. All right, so what this is also getting at is Le Chatelier's principle. And this kind of sounds, I think it makes things more complicated. But all this is kind of saying is, can we predict, how our concentrations of reactants and products will change? Can we predict which side is going to favor reactants or products based upon the stresses? And so basically, the issue is if you have a system at equilibrium, then it's going to shift to minimize the disturbance. So again, we'll kind of look at what that means. And obviously, if you disturb the system, you make the system open and introduce a new factor. So then it has to re-establish equilibrium. And so let's look at, because this gets kind of wordy, but if we pair this with a chart, it will make more sense. So let's look at adding reactants, but let's look at our chart here. And so let's orient ourselves for a second. So we're looking at N2O4, and it's decomposing into two equivalents of NO2. So this is a dimerization reaction, equilibrium. And so now we're looking at the initial conditions. So right now, this graph is just our initial equilibrium condition. So it's already at equilibrium. And all this means, right, is it's the same amount of, our amounts of N2O4 and NO2 are not changing, right? So they're still reacting back and forth, going back and forth, but overall our concentrations are remaining the same. So that's all we mean at equilibrium. And so now, let's see what happens. And so in this case, let's kind of flip our, so in this case we added some, let's look at this case. I actually want to look at this case just because this one is formally our reactant, so it kind of follows what we were saying textually. And so they're at equilibrium. And so now here we added our reactant. And so kind of look at what happens. So we artificially added our reactant, and so of course that's going to start decreasing, because if we add a bunch of N2O4, now that's going to drive it to the right, so to the opposite, so away from this. So right, it's trying to mitigate that effect. So basically it was happy at equilibrium. You dumped a bunch of excess reactant in, and so now it's going to favor more product generation. And so we see that in our little graph. So now if we disturbed our equilibrium, well, now we have to make more NO2 to account for that. And so notice, right, your new equilibrium is then reestablished. And so if we were doing this more mathematically, I would make you calculate this, but I won't. But essentially, right, your K then is still the same. So you get a new K, but it just reestablishes, right? And so you consume some of that added reactant, and then obviously that makes more product to, again, establish equilibrium. And so that's all that's saying here. So, right, you add your reactant, and of course we'll look at this. So as long as it's not a solid or a liquid. So if you have like a solid pile of carbon, that doesn't change your reaction rate since it's more of the surface reaction. So adding big blobs of solid does not change your equilibrium. Same thing with like liquid. So this would be if you added like a liquid reagent. So that could be confusing. And that's going to be like super concentrated, so that doesn't affect your rate. It's only if it's aqueous, like a molarity. And so how does this affect your rate of your forward reaction? So adding a reactant initially increases your rate, right, because you have more of your reactant, but then it will, again, restore equilibrium and no initial effect on the reverse reaction, right, until you start making more NO2, and then it will go back in reverse. So how does it affect the reverse? So at your new equilibrium position, right, now we have more products than before and less of the non-added reactants than before and less of the added reactant. And so all that's saying, that was a really confusing way to say, right? Well, we consume some of this artificially added reactant, so it reestablished new equilibrium, but we still have more than before because we added a whole bunch. But then to compensate for that, right, we made more product. So that's all that's saying, kind of wordy. And then again, right, K itself is not affected. It just helps you tell you what the equilibrium is. And again, it's at that temperature. And so that is something about K. Again, we won't do that in this class. You could take my 200 level series if you want to dive deep into all of this. But basically, this is temperature dependent. So if you change your temperature, that can change your equilibrium value, but then you just have to remeasure it, basically. Or there's formulas, like I said, that correlate, but not for our interest. All right, so we'll stop here. So we'll continue back on Wednesday with Le Chatelier's principle, going through all this. So we'll take our 10-minute break. I need to find where I slapped your quizzes down. I know I printed them out this morning. And then I'll also print out the homework because I forgot about that. So I'll get those. So, quiz in 10 minutes.
Yes. Your day one? This is chemistry, right?
Yeah. That's right. wait. Hey, I have a different day this week. I actually have Friday off, which I normally don't, but you're not available Friday.
I'm completely available right now. For like this entire month, because my son is up in Washington with his mom.
Okay, so Friday at noon.
Sounds good.